Hello together. Today we want to program the ADC with the nRF Connect SDK, and our developer board we want to read out the sensor value. For this we are using a light dependent resistor, and this gives us back an analog value. I mean, the most sensors today working with something like a bus system like I²C or SPI or whatever, so we get directly digital signals back, but it's not always the case, and it's always necessary to know that also in these sensors we have a kind of measurement chain. So we have our sensor, and then there is like a signal modulation, like fitting to the voltage of our ADC. Then we're having a sample and hold, so we have to hold the signal for a short amount of time so that we can convert this, and this makes then the AD converter. Here makes from the analog signal a digital signal so that we can use it with our PC or microcontroller or whatever. And this is also inside of an I²C sensor, for example. We're having there always a resolution, so we cannot, when we're having an analog value, we don't get every value back, so we have a resolution. For example, when we're having 4-bit analog values, then we are having only 16 possible values which we can get. So when we are having then a value from 0.6, for example, we get then back 0.5 only. The nRF Connect SDK, like the most microcontrollers, have a successive approximation analog digital converter. It's mean over more steps, becoming nearer to our measurement result. So we're starting, for example, here we're having around 0.8 our measurement value, and we're having a range from 4 volt, and we're starting then with a half of it and comparing it, and we're seeing 2 volt is too high, then we're taking the half of it again, saying 1 volt is still too high, then we're going to 0.5 volt, it's too low, and then we're going to 0.75 volt, and then we are already quite near. This would be 4 steps in this case. And the ADC in the nRF 52840 is this kind of ADC. Our scheme, what we are using is a light dependent resistor, and we are having here like a voltage divider, so we are using a 10 kilo ohm resistor and a light dependent resistor here, and connected with a voltage supply with a plus here and with a ground here at this side, and in the middle we are taking the value and putting it to our analog digital converter, so we are measuring from here the voltage, and it depends on when it's lighter, then the resistor is lower, and when it's darker the resistor here is higher, so we're getting different value here. Our nRF 52840 microcontroller has altogether 8 channels, so we can make 8 different analog digital conversion. They will not be done parallel, they will be done in a row with a multiplexer and so on, but we will not realize this. We can use 8 of them, and to this we have also 8 ports or pin. We have to differentiate it with channels. It's not the same, and we can choose which port will be connected with which channel. So we're having here the ADC ports analog input 0 to 7, and the pins which are say belonging are pin 0, port 0, pin 2 for example, for analog input 0. Yeah, we will use also the first one for connecting our LDR. But these are the pins, and we cannot use every pin on the microcontroller like normal for GPIO. We can choose, we are more free to choose. Here we're having these 8 pins. How we are connecting our LDR to the microcontroller, to our developer board. You can buy such a cheap resistor already. Yeah? So a light dependence resistor costs a couple of bucks. You see here the LDR and also the resistor for the voltage divider, and plus, minus, and then we are connecting it to port 0 on pin 2 in our case. For the programming, we start as usual. We are making a copy, in this case from the Blinky example. Call it my ADC example. Deleting the build and starting Visual Studio. So I'm adding the application. Make a build configuration. And afterwards open the application. The first thing what we have to do is of course adding here the ADC library, yeah? So that we're having the function for the ADC. And how we program it now, like usual, we are needing a node. We're having an ADC node. And the rest here I delete. Don't need this. So. And here we have the ADC. We're seeing here what's the name of the node. We can also take a look in the device tree. So we're having here our ADC, and you're seeing here also the name from the ADC, yeah? And it's okay. We can directly use it. So the next thing what we have to define are the properties, how we want to use it. So we're making macros for this. We are using a resolution from 10 bits, which means we're getting 0 to 1023 as result when we're converting it. So it depends on what kind of voltage we're having as input, and then we're getting a value from 0 to 1023. We're using the channel 0, and as port we are using analog input 0, like I showed you before. We're using the ADC reference, the internal reference, so we have to compare it with something, and the internal reference is with the nRF 52840 0.6 volt. And as gain, so as multiplier, we are using ADC gain 1.5, which means we multiply this with 5. This means our input, we compare this 5 multiplied with 0.6, so this means with 3 volt. This fitting because the supply voltage for the sensor is maximum 3 volt, where we plug in the VDD on the board. So, and now we have to configure the channel. There is a variable which is called ADC channel config, and yeah, then maybe I use the name channel 0 config, because we can have a channel altogether, and there we are defining the gain, the reference, so we're having here the internal reference, the acquisition time, we're using here the default time, and the channel. And here we also have to select the ports. This is also special for our microcontroller. This is why it's in a if-def in comparison if it's an nRF as a ADC. There is an input positive and an input negative. When we're defining also an input negative, so we can define the second ports, then we will have a comparison between these two inputs. But I actually want to measure only one, and for this I define only one ADC input. The next step is then that we are needing a buffer for the readout for the ADC sequence. First we are defining a sample buffer. In this case it's an int16 value an area, but with a size of 1 only. We can use here a bigger area, so it depends on how many channels we want to read out. But since we want to read out only one channel, an area from the size 1 is for us at the moment here enough. And also the ADC sequence, which we have to adjust, we are using only one channels, and this is our ADC channel 0. When we want to read out parallel in one command more channels, then we have here to add an OR and add there another channel like bit ADC channel 0, ADC channel 1, and so on. So this is an int value or int 8 value where the bits are set which channel we want to read out. Then as buffer we are giving our sample buffer and the size of the buffer and the resolution. In the next step, in the main function, we're checking then if our device is ready, and if the ADC is ready, we go on. And for this, we are making a setup from the ADC. We're checking if there is an error, so we are making ADC channel setup and giving our configuration, which we make here before, on the ADC device. I have to be careful because I changed the channel to channel 0. And in the next step we can actually directly read out the channel, the ADC. So with this we're making an ADC read with our device and with the sequence which we defined before, and since we define only one, there will be after this in the buffer in our array will be send the value. And now with the value, of course we're having the integer value directly, which we will print out, so it's in the sample buffer at position 0. And here I'm getting the internal reference, so the 0.6 voltage as integer value, so it's multiplied. It's because we set it here to internal, the reference, but I know it's at 0.6 when it's internal, but when you're looking here, it's just an enum, yeah. So it's, I don't know what kind it's for. So from this we can calculate the voltage. But there is a function which is called ADC raw to millivolts, and there we needing the ADC VREF, yeah. And we also give this gain and the resolution and my value, and then we getting out in my value the result in millivoltage, and I print this here out too. I forgot, of course, because I want also the ADC value. Since I'm overwriting it here, I will not have this value anymore, and of course I want to see the original value also. Yeah. Then I can directly compile this. Got an error. Because of what? What did I miss? So yeah, okay, I did a big mistake. Good that you see it, because when you're seeing something like here, of course we have to activate first the ADC, yeah? Config ADC to yes. If not, it will not be available. So we're going back, now we build it. Transfer to our board. Connecting to our COM port, and you're seeing that we're getting here out the ADC value and the voltage directly converted. And when I show you the board, you see I built here up one by my own. It's an LDR, and here is a resistor 10 kilo ohm, and I just connecting like I described it before. When I put now my finger here, you're seeing it's raising also the voltage which we are measuring. Yeah. There is what I want to mention, maybe when you look in the documentation, this is a lot what we have to define again as macros, and since we're having a device tree, it could be much more comfortable. And I was falling in this trick actually before. When you're looking in the documentation, you see that you can directly define at the ADC channel 0, and you make the configurations that you what you want here, and there are then a macro like ADC channel configuration, that we get them here from the DT, or even there is also ADC DT spec-get, so where we can get all information directly in one file. But yeah, this is in version from the Nordic SDK 191, not included yet. It's in the new version, so this is in the new Zephyr version. So it doesn't work yet. When there is out a new version, I guess then it's already included. And it's a little bit more easy, and we don't have to define it here. This was a short introduction into the ADC with the Nordic Connect SDK. If you like the video, push the like button and see you in the next video.